So we'll wait for some time, like 2 minutes or something, so that others can also join here. Then we'll start with this. Anyway, this session is recorded. It will be. I will be recording this session and uploading this on YouTube. So, yeah. So the people who are not joining, they can see this after this live session. So today we will be discussing about the topics which were being discussed in the week 3 of this OPAM Practical Application Design Simulation and Implementation course of NPTEL. So before going to this week 3 topics, I would just like to go through what we did in this week 2 live session and what happened in this week 2. So there were some previous session doubts. We clarified that those were on bias current and all. So then we saw the effect of slew rate and the bandwidth of on OPAM. Then we learned about effect of loading in different configurations like inverting amplifier, non-inverting amplifiers also, and then realizing using a buffer. Then we also realized a half wave rectifier and a full wave rectifier also. So yeah, so these are also called as precision rectifiers. Then after this we saw also practical diodes, like what is the use of practical diodes, like how they behave in this half wave rectifier or full wave rectifier things. Then we saw clippers, positive clipper and negative clippers. And then after that, like we discussed, I gave some hints to solve assignment week 2 questions, and then we discussed some questions, some extra questions after that. So now today in this week 3 we will start with the first topic which was being taught in this week 3, and that was I will write it down for you. So that is op-amps using clampers. So we will realize clampers. We realize actually clampers using op-amps. So how we did? We'll go through it. Clampers using op-amp. So what is a clamper? Clamper is basically in one word we can say a DC restorer or DC inserter. As why we say that, because it introduces some DC into the output voltage. So basically, it can shift the whole wave through a DC level. So that's why we say clamp. Clamping itself, the action, we say the clamping action itself, a clamping like holding something and putting somewhere else. So that what clamping is all about. So that is like what clampers means. Then we will come to, then we have like positive clampers and we have negative clampers. So positive clampers will shift the DC level to the positive side of the output, and the negative clampers will shift the DC to the negative side of the output. So just for example, we can have, if we have a waveform like this, so it can clamp this waveform to the positive side. So this is V output, this is V input. Similarly, for this input waveform, if we have a wave like this, it can clamp it to the negative side of this, like this. This is V output. Okay, so this is V input. So now I will talk about I will talk in detail about how this positive clamper works, and you can apply the same logic in the negative clampers. So there are many things going on this positive clamper. So first, we will make the circuit for that. So I will be discussing here about positive clamper first. And negative clamper, you can like logically you can explain its working, but I'll be explaining the working of this positive clamper. So then this, like, we have a circuit, uh, we have a voltage source, we have a capacitor, then resistor, then an op amp, and we use a reference voltage realized using a potentiometer, we can say, which is being, the voltage is being divided using the reference voltage VCC, sorry, the supply voltage VCC. So this is the V reference, if we talk about, and we have a diode here, D1. This is the feedback, and this is the load resistance RL. Yeah, this is Vs, this is C. Okay, so, and this is one resistor R. So like in that week we saw this resistance to be 4.7 k. So this resistance we normally take so as to avoid the like excessive discharge through the capacitor. So I will write this also. Uh, we use this resistor to avoid excessive discharge through capacitor C. So like we want this capacitor to be holding that charge for long so that we can realize this positive clamper. That's why we use a resistor R here. So it will not easily uh, will be discharging this capacitor. So the charge will be there for a long time on the C. So yeah, so we'll go step by step how this clamper works. So first we will be like, there are two sources, there is one Vs and there is one V reference. So we are applying V reference from here, we are applying Vs from here. So let's say we use superposition principle. I am now analyzing this circuit in more detail so that like you can get an idea, you can have a feel like how this circuit works. Okay, so first I will be just considering V reference as a source. Like Vs, we can make it ground. So by using superposition principle. So using, just to analyze this circuit, that's all. So using superposition principle, yeah. Okay, so considering Vref only, Vref input volt, Vref at the positive, this one, this only we are considering first. Okay, so what will happen? So if uh, Vref is greater than 0, so since we don't have Vs here in this, in first case, so Vref, if it is greater than 0, then the non-inverting side of the op amp is having a more voltage than the inverting side of the op amp. Then the output of this op amp will be positive, and thus the diode will be in forward bias. So we can say VOA. This, let's say this is VOA, okay, and this was our V naught. So VOA is positive, okay. Then diode, thus that implies diode is diode D1, diode D is in forward bias, D1 diode, okay. Then then this circuit will act as, then this circuit will act as voltage follower, simple voltage follower. So, what does voltage follower then do? It simply, whatever the input voltage is, it reflects at the output. So we will get V naught equals to Vref when we have Vref greater than 0. Okay, this is one condition. Now we will consider the effect of only the sinusoidal input. Okay, considering considering we can say V naught prime, because after in the end, as we are using superposition principles, because of Vref we will get V naught prime some voltage. Okay, so V naught prime will be Vref. So considering, now we are considering Vs, the source, the sinusoidal input, and thus we are not using here V reference voltage. Okay, so then what will happen? We'll again consider two cases. First case, like when Vs. So for the convenience, I will just draw the waveform here. Like we will follow this waveform throughout our analysis. So this is the input voltage. Okay, this is Vs. We have this. Then, yeah, then we have Vc, the voltage or the capacitor. Vc is the voltage around across the capacitor. This one. This is Vc. Okay. Then we have. If you have any doubts, you can ask me and you can interrupt me in between. So yeah. So Vc is there, and we'll also simultaneously we will draw V output. Okay. So how it will be then? We'll see. So let's say we have this as Vm. This is Vm, the peak voltage, and this is minus Vm. Uh, Now, so we are considering first case where like V1 or like we can say Vs is greater than 0. This first case, this one. So when Vs is greater than 0, so what will happen? Let's analyze this circuit. When Vs is greater than 0, so this voltage, I will use another, okay, I will use same pen. So the negative side of the op amp, okay, the negative side of the op amp will be this side. This side will be having, because now we are not considering Vref, so Vref here it is 0, as we are using uh, superposition principle. So Vs, it will say, so Vs is obviously greater than the positive side, like whatever positive Vs, it is the negative side in the inverting interval of this terminal of this op amp is having more voltage than the positive side of the op amp, as positive side is having the 0, it is at ground, since we have considered Vref 0. So that means VOA equals to negative. Why? Because this is at more potential than the positive interval non-inverting side. So VO will be positive. Okay, it will be acting as an inverting amplifier. So this D1 will be what? For reverse biased. Okay. So D1 will be reverse biased. So D1 will be reverse biased. Till now it's okay. Now, I will just mark one more thing, or I will make this circuit again. Okay, I will do this again. So this is V plus, this is V minus, this terminals. So V plus. So then, yeah. So we know V plus equals to 0 volt, as we have not considered Vref here. So Vref is 0. So V plus equals to Vref, and it is 0 here. And what is V output? V output will be V in, this we can say double prime, because we are considering only Vs here. So V in plus Vc. Okay, how it is happening? I'll make a circuit for you. This is our voltage source. This is a capacitor. This is a resistance, and we have a diode here, and this is grounded. This is reverse biased diode, so we'll open it, and this is RL, and this is V naught prime. Fine. This is Vs. This is C. This is Vc. Okay. So V naught prime. This is V naught prime, as we got. This is V naught prime. So V naught prime will be what? V in. V in is basically Vs equals to V in. So V in plus Vc. Fine. So we got this V naught prime double prime as V in plus Vc. Now we have taken one assumption in this circuit, that since the assumption is RL. See, this is the time constant for for this thing. This is the time constant. So RLC is very large. Okay. So capacitance will not able to charge in this cycle. Capacitance will not be able to charge during this cycle. Okay, during this period, like in the cycle or period. Now, so what then? If capacitance will not be able to charge, then what will happen? The VC, the capacitive voltage on the capacitance will be 0 volts. Fine. Then what will be V naught double prime? As we see, V naught double prime is this. So this went to 0. VC equals to 0. So it will be V in only. So whatever input voltage is, we will get that the same at the output. So for this, I will update this waveform here. Since we get at the positive cycle, we get 0 voltage, and we got V naught as equals to Vs. So we got this. Okay. Till now, it is fine. Now, we'll go for the second cycle, that is the negative cycle, from pi by 2 to pi, and this is 3 pi by 2. Okay, so this is, yeah, so till now this is fine. We came to know, okay, the output voltage is same as the input voltage when we consider Vs greater than 0. Now if we consider Vs less than 0, this is the second case. I'm parallelly discussing. Let us make a diversion here, no confusion. So when Vs is less than 0, so what will happen? Yeah, so wait. Hmm. So then what will happen? If Vs is less than 0, then this voltage, the negative side, the inverting terminal of the op amp will be less than the inverting terminal of the op amp is less than the non-inverting terminal of the op amp, as we are considering Vs less than 0. So that what will happen? The VOA, this VOA voltage will become positive. Okay. This is simple. VOS, like throughout these 2 3 weeks we are learning this. If non-inverting side of the terminal is higher than the inverting side of the terminal of the op amp, then we get the positive output. So this will be VO equals to positive. Okay, that will make D1 in forward bias. Okay, this D1 will become forward bias. Now, since this is forward bias, now the op amp is having negative feedback. Negative feedback. So here we can use virtual short concept. So we can use virtual short concept here. In this case, we cannot use virtual short concept because this was having no feedback. Now, but here we can use virtual short. So using that, what will happen? First, I'll make a circuit for you. So the circuit will look like this. It will be this, and then an op amp minus plus, then this is this one, and we have RL, this is there. So this is Vs, this is Vc, okay, and this is R. So this is V minus, and this is V plus. This is V naught double prime. So what will happen? This is V naught double prime. So V plus will be 0. We know V plus is 0 as we have not considered V reference voltage, which is now once virtual short is there, so V minus will be also 0, and that since this is a voltage follower circuit, so V naught double prime will be also 0. Okay, in this case it will be 0. So V minus, or we can say V naught double prime, will be equal to Vs plus Vc, this voltage, Vs plus Vc. Fine. And V Vs, because we know that yeah, so this is V minus, so V minus is 0, so Vs will become equals to minus of Vc. Fine. So Vc, the capacitive voltage will be equal to, so in this stage capacitor will start charging and it will charge till minus Vm, because here capacitance will start charging, as circuit will look like this. See, circuit will look like this. Since it got a path from the output of the op amp, so it will look like this. So there is no resistance uh, which will create resistance in making this capacitor charge. So since we had a negative polarity here, because we are talking about Vs less than 0 in this case, okay. So this is plus minus, so we will get a charge plus minus here Vm. So this is Vc. So Vc, it will look like this. So it will be like this. Now, so this is happening till 3 pi by 2 cycle. Till 3 pi by 2 cycle. This one. 3 pi by 2 cycle. I will tell you why. Because after this, because here, like the input voltage is increasing in the negative side and keep on increasing and it reaches the minus Vm potential. And the capacitor got its minus Vm potential. So we have Vc equals to minus Vm. Now V negative, the inverting side of the terminal, or we can say V naught double prime is equals to V in plus Vm. Since capacitor got this Vm, so okay, I'll see. I'll just erase this now. Now this is Vc, so it will be V in plus, since the capacitor got the Vm potential, so we can say V in plus Vm. So now when this V minus become V in plus Vn, then what will happen? Then after 3 pi by 2, this Vn start decreasing. So this, but anyway, this is start decreasing, but anyway, this whole potential will be positive because we have Vm and this is decreasing. This is less than Vm, Vn. So the whole value will be positive. It will not be negative. So what will happen? So V negative will be positive and V plus is 0. So that will make V minus greater than V plus. So this will make this op-amp to work in. Op-amp will then work in, will make this diode what, again reverse biased. Okay, because we got V minus become greater than V plus, so this will be VOA will be negative. So VOA, no, VOA will be positive. Sorry, VOA will be negative. Yeah. Uh, it comes in. Yeah. Oh, wait. Oh, okay, yeah, yeah, yeah. It is positive. So it is positive. V minus is positive. So finally we got the this whole thing is positive. So this is greater than the no, non-inverting side of the op amp. So finally we got the output that implies VOA is negative. Okay, so then VOA is negative. So this diode will be in reverse biased. Diode becomes reverse bias. So then V output, then VO double prime will be what? It will be V in Vs plus Vc. We know that, but now it will now become V in plus Vm. And since this now this V in, the input voltage, or we can say Vs, is never is it can never okay, so yeah, this Vs voltage can never be more than this Vm. So what we'll get, will this diode will remain in reverse bias. Diode will remain in reverse bias. So then our output waveform will be for three. So till from pi by 2 to 3 pi by 2, what we got? We got till 3 pi by 2. Yeah, we got V naught to be 0 volts. So we have 0 volts. And this VC, it became charged to minus Vm. This is minus Vm. Okay, then after this V naught prime double prime is Vs plus Vm. So this Vm is being added to this Vs. So what will happen then? This will start increasing from this side. This is Vm. Now it will follow this path. This one. It will never go down. And this capacitance will have for if we talk about ideal condition, this will be almost constant. This value. Although it will be decreasing in reality, but it will be always constant, and V naught prime will get this one. So basically, what happens? This equation is important. We added a DC. This is DC, okay, and this is DC, and this is what sinusoidal input, sinusoidal supply. So we added basically DC to this VS. So we got a shifted waveform. So now, but we since we use the superposition principle, then what happened? We also have to consider this Vref, which we initially used here. So now combining, now the what will be the final output? V naught will be V naught prime plus V naught double prime. This is because of Vref. This is because of sinusoidal supply. Sinusoidal supply, that is Vs. Okay. So what will be the waveform? Waveform will be, this will be equals to Vref plus Vs plus Vm. So we got Vs plus Vm plus Vref. So our DC, so the total DC added to this Vs is this Vm plus Vref. So basically our waveform will shift to this potential. So this will be Vm plus Vref, and this is V naught. After superposition, I will write it after superposition. Final output voltage. Final output voltage. Okay. So this is the equation. So this will be Vm plus Vref. Now, when you saw, if you would have taken the lectures on week 3, so we saw in that like the output waveform was getting saturated, like it was getting blunt in the ends. So you would have seen we were setting, so in week 3 lecture, in week 3 first lecture, first lecture on this clampers, what we observed, we observed the waveform, output waveform as this. There was a blunt end like this. So this, although we shifted this to Vm plus Vref, so this was there at the output. So but why is there, why it is, why it was there, why we got this uh, like clipping action here? So this, if you can think, so this why we got, because we know V naught is what? V input plus Vm. If so, yeah, if this is V input plus Vm, so this signal, okay, this signal is where? This is at, I'll draw here. This signal is at this point, and we have here Vref. We have V in plus Vm here. So this is a diode. Okay, so when if V in plus Vm ref is less than Vref, I will say if it is less than Vref, what will happen? This will become positive. VOA will be positive. Then D1 will be forward bias. But we said that now the diode is in reverse bias for throughout the operation. So that's why we achieve this shifting action. But here in this case, since D1 become momentarily forward biased when this V in plus Vm become less than Vref. So at that moment, what happens? If this become forward bias, so it will act as a voltage follower, and our output, which is V minus, will it become Vref. So it will be virtually short. Virtual short will happen, and this whole thing will be equal to Vref. Okay. So this virtual short will dominate this V minus, and we'll get V output as Vref. That's why this point is Vref here. So for a positive clipper, if so to summarize this thing here, for a positive clipper, if the signal let's say this was Vref, if the signal is going down than Vref, then it will be equal to Vref itself. So a clipping action will happen. And for negative, it will be for the negative side of the uh, this waveform. Okay, for this is for positive clippers. So this all I talked about positive clippers. So by just this understanding itself, you can derive this thing for the negative clippers also. Okay, so this was the thing. So this is how this we analyze the clampers which were being taught in the first lecture. Okay, any doubt in this? You can ask me. So this was there. Yeah. Then otherwise we'll move to the second topic what it was. So so the lecture two talked about the ranges of op-amp. Okay, ranges of what do you say? Ranges of feedback amplifier basically. Feedback amplifier. Since we give feedback to these amplifiers, ah, so there are like some we cannot like simply get the gain at what we want. So it is depend on some value. And what is that value? It is the first of all, if there are two values which are deciding that. First is the plus minus V supply voltage, which we are giving to op amp. So since this op amp is being run by these two supplies, so we cannot get a gain beyond this. Otherwise, it will be a violation of law of conservation of energy. Okay, if you are giving 5 volts, how you can get 6 volts? Got it? If you are giving supply as a 5 volts, you cannot get more than that. Although it can amplify your 1 volt signal near to 5 volt, but it cannot make it more than 5 volts. So this is one thing. Another thing is this range is also being what we'll say been restricted by the gain bandwidth of the op amp. So we have seen. So now then there were two experiments in which we gave some input. Input was given to the op amp, and that op amp gave an output, and there was some gain. So output was gain, as we all know, gain into input. This obviously the differential voltage across the op amp. So this was the gain. So this was the output. So what will happen, like if this will become, if v naught is greater than v sat, or we'll say v supply, then v naught will be equal to v supply. But in practical op amps, we don't see it is equal to V supply voltage. It is minus some voltage, and this all is This is voltage swing. So this is because of the output voltage swing. So we get final some voltage which is equal to output voltage swing. Output voltage swing. This voltage is equal to V output voltage swing. Okay, V V naught. Fine. Now we saw. Now this in this case we kept on changing the V input. Okay, and also the gain and the gain. But here in this experiment, this was second experiment. This was first experiment. In second experiment, what we did, we actually changed the frequency. Changed the frequency. Then what happened? Uh, so we kept on increasing the frequency. So we all know that the open loop characteristics of an op amp is what? It is like this. So it is a low pass filter basically. All open loop characteristics are low pass filter for an op amp, and this is because of the internal capacitance and resistance in the op amp. Okay, so these are all basics. So yeah, some FC is there. So there is some point where we get a 0 dB gain. And what is 0 dB gain? That is like gain equal to 10 by gain equal to 1. So if we will keep on increasing this frequency beyond this, then the gain will be, then gain will decrease. So although we were giving, let's say, 1 volt, our gain was, let's say, equal to 2. We wanted to achieve 2 volts as the supply voltage we were giving, let's say, 5 volts. So there was no limitation of output voltage swing also, and the limitation of supply. Then also we won't be able to get this 2 volt outside if the frequency is more than the gain bandwidth frequency, this fc, this f, or you can say f naught, or you can say, because the gain of the op amp will decrease. It will decrease to 1, decrease less, it will become less than 1. So the amplifier will not be able to act as a amplifier. Op amp will not be able to act as a, will not be able to act as an amplifier. Okay. So here this was one more limitation. So when you are designing, when you are working with the practical circuits using op amps, you should consider the supply voltage, the gain bandwidth also. So this bandwidth is very really important. So yeah, so this was in the lecture 2. Then after that, we talked about oscillator circuits. So from lecture 3 to, I think, 4 lecture, yeah, 4 lecture 3, we talked about oscillators. So we'll one by one, we will just go through that oscillators. Okay. So op amps as a phase shift oscillator. This thing. This was first topic. So, uh, why op-amp? Why we need? First of all, why we need these oscillators? Why they are used? And so basically, oscillators can be used in, we say, clock circuits, like where we continuously want to generate one signal, one constant signal, we can say, clock signal we can use, or we can, like, or we can simply say sequential action. We have to controlling. So yeah, controlling sequential actions, sequential actions, and synchronizing, synchronizing various stages. So for all this, it is use oscillators are used. We also came to know that these oscillators work in positive feedback configuration. And there we'll learn also there are some oscillators which works in both negative and positive feedbacks. One example is Wien bridge. Okay, yeah. So, but it is being mostly dominated by the positive feedback. So that's why they become oscillator. So finally, the circuit which is being dominated with the feedback circuit, whichever feedback circuit is dominating that op amp, it will behave like that. So here positive feedback is dominating, so that's why it will behave as an oscillator. Fine. So yeah, in this, then basically, uh, so what it will do, it will basically convert, uh, it will convert DC input into AC signals. So why we said DC? Because we are giving plus minus V supply. It's not like that we are not giving anything. We are giving the supply. Then based on that supply, that is the inputs to the this terminals, the supply terminals of this op amp. We are giving plus VCC. This is minus VCC. Although in the input we are not giving anything, but here we are giving. So based on this, what happens, there is vibrations in the register, the input side of the register. Because of that, there is slight differential voltage created in this op amp. This all being taught in peak 1. So there is a slight differential voltage being created in op amp, and then it starts slowly giving the output, and then we finally start, the output start on increasing. Okay, keep on increasing, then this feedback action comes into picture, and that it maintains that oscillation. So that is how it works. Okay, so basically it is converting DC input into AC signals. Fine. Then so we can, yeah, so this was the case. Then Yeah, initially we have to, this is also important, initially we have to keep the input gain open, or we can say open loop gain slightly greater than, slightly greater than what, 1, so that it will, initially it can get the boost, then later on we can maintain this of using a feedback. Okay, so then we talked about Barkhausen criteria. So before that, I'll just give a layout of how an amplifier looks like. A basic amplifier, we give a V input voltage. We have a summer here, which is actually doing differential thing. This is an amplifier. We get output. We feedback this output, and via a attenuator, we will say, which gain is beta. We get V out into beta. This is the feedback voltage for this path, and we have this gain. So here this is subtracted from the input voltage. So we get V input minus V out beta. Fine. So this is then again fed back to amplifier, and this keep on like keep on rotating like this. So we had gain without feedback. Without feedback, if we say, what will be the gain? This will be V out simple by V in. So whatever the input, V out by V input. So then with feedback, what will be the gain? What the gain becomes? With feedback, we close loop feedback, we get the gain A upon 1 plus A beta. Okay, this is closed loop gain. So now to be to keep this in a positive feedback. So this is basically for negative feedback. To make it positive feedback, we need gain to be looking like this: a upon 1 minus of a beta. For that, this should be modulus of a beta should be greater than 1. That is what Barkhausen criteria is. Okay, this we also learned. Fine. Then after that, what we learned? We learned phase shift oscillators. Phase shift. So we are now coming to the one first oscillator. This was only the like basics. Then what actually phase shift oscillators are? So we'll first look at the RC phase shift oscillators. First is RC phase shift oscillators. So we need this phase shifts. Why we need phase shifts? To meet this Parkinson criteria. That's why we need this phase shifts. And that's first we can realize with RC phase shift circuits. Phase shift circuits. Okay. So these are normally used for low frequency ranges. And we have LC phase shift circuits also that are being used for the high frequency ranges, low frequency applications, you can say. Okay, so then in this, what happens? We have this. We have a negative feedback amplifier, inverting feedback amplifier. We are grounding this. This is RI, and this is RF. Okay, so now what we know, so whatever input we will give from this side, so it will be making it 180-degree phase shift. That what an inverting amplifier does. So but we need a 0-degree phase shift, 0-degree phase shift to meet Barkhausen criteria. So how we will achieve this? So we will achieve this with this, like this thing, by using CRC circuits. So normally each component of RC, we can say, can give 90-degree maximum phase shift. But since there are some practical limitations for its capacitance and even the resistance also, so we prefer to get this 180-degree phase shift from three RC circuits. So one will give 60, another will give 60, this will 60, total will add on to 180. So we'll then feed back this to this. So uh, this will be a 0 degree phase shift finally. 0 degree phase shift. 180 here, 180 here, total 0 degree phase shift. So we can meet this Parkinson criteria. So we also came to know that the frequency was 1 by 2 pi RC into root of, basically it is 2, and n is the number of RC circuits being used. So here it is 3, so we get 1 by 2 pi RC root 6. Okay, this was the frequency on which the circuit will operate, on which the output will be generated for this frequency. Okay, so this was there. Then uh, yeah, so we talked about this, and then we also talked about Wayne bridge oscillators. Wayne bridge oscillators. Oscillators. So this was Wayne bridge oscillator. So here, like, we are using RC combinations, but in one in parallel, one in series. This was the configuration. Okay, so this circuit works in both negative and positive feedback conditions. Okay, so this is negative, this is positive, and this is R, this is C, this is C, this is R, R3, R4, and R1. Yeah, this is V naught, and we have this. So we have a positive feedback also, and we have a negative feedback also in this circuit. So yeah, this was the Wayne bridge oscillator, and the frequency of this is given by 1 by 2 pi RC. This is all you do this, you did this in this week 3 lectures. And then we have Hartley, then we will talk, then we came with Hartley oscillators. Hartley oscillators. Okay. So then what are Hartley oscillators? So these are LC tank circuit based oscillators. LC tank circuit based oscillators. Okay. So this how it looks like. So it is basically combination of inductor and capacitances. So here only one capacitance is used and two resistors are used. So this was the configuration for Hartley. We look this, and this is plus minus. This is again an inductor. This is the output. CL. Okay, here it is resistance. This is resistance. Okay, RF, L1, L2. Fine. So this was there. So there was like a coal pit oscillator also. I will just tell this circuit for coal pit. Coal pit oscillator. So here, by the way, frequency was given by 1 by 2 pi. Uh, this one LTC. LT is what? L1 plus L2. Okay. In coal pit oscillator, we use two capacitors instead of one, as we use in RV. So it is like this. So this was there. Resistance is minus plus. This is resistor feedback resistor. This is V out, and then we have capacitor, two capacitors here. When fed back to this L1, R1, this is R2, R3, C2, and C1. Fine. So these were all about oscillators which we read in this. Later on, we will be implementing this in the further lectures and further weeks, future weeks, I can say. Then now there were some assignment questions also. So um, these are now the assignment questions were simple in this case. Like we had like, okay, now I will discuss about the assignment questions first. So I'll add some pages in this. Wait, assignment questions. Edit page and let's say I add 4 pages. So till then, this was the week two, week three, week three. Now assignment questions. I think the due date is over, but still, we'll discuss these assignment questions for the better understanding. Assignment questions, but I will not. Anyway, I will not give hint. I don't know whether you have the answers or not. I will only give the hints, not the answers. Assignment questions, week three. So, question one was about. I'll just see here. So, a three-phase RC oscillator has a target frequency of oscillations. So we have a frequency we already know, and select the correct combination of resistors and capacitors value to realize the mentioned frequency. It was simple. We know the frequency. It was 13.831 kilohertz, and which RC oscillator. So they are saying three-phase. Three means three-phase RC oscillator they are using. So for that we know the frequency formula 1 by 2 pi RC. Since it is 3, so it will be root 6. It is simple. You can just input the frequency value, and you can get the value for RC, and based on the options you can get the combinations for them. Okay. So this was question 1. Question 2. So question 2 was uh, why LC tank circuit is not used as an oscillator in practical circumstances. So there was some oscillator inductor coil has some resistance, capacitor has some leakage based on dielectric, or both of them, or LC tank circuits can be used for all practical oscillators. So I'll just give a hint, like everything in this world is can never be perfect, can never be perfect. So based on that you can get to the answer for this question. Anything, or we can do anything in this, yeah, everything in this world can never be perfect. If it is perfect, it will not be existing here. Okay, so this was question 2. Then question 3. Question 3 is there. Then question 3, what question 3? So question 3 was saying, you have seen the working of the clamper circuit in the lectures. Okay, we have clamper circuits. Okay, looking at the way the circuit functions. So what does then clamper circuits do? So I already told like what it was doing. Was it a leveler? Like leveler, I will okay tell about these things. So blocker is mean basically blocking something. So cutter is basically cutting or clipping, you can say. Inserter is basically like inserting some DC voltage to the like the output voltage, and or DC leveler is like leveling that thing, like making big or coming making the output signal to come to a level, like some threshold level or something. So that is a so based on that you can easily do this. Then the next question was, an Opamp amplifier circuit is working in a closed loop mode. So they have said closed loop mode at plus minus 15 volt supply. So when the gain is 10, so they have mentioned the gain was 10. Okay. So then for an input voltage of positive half cycle, so positive half cycle swing of 1 volt is there, and the output swing is 10 volts as per closed loop gain. So okay, yeah, that is correct enough. So we are giving 10 volts. Sorry, the gain, if it is gain is 10 and input is 1 volt, will get 10 volt output. That is what they are saying as per closed loop gain. Now the gain is adjusted to 5. Now the gain is equals to 5. Okay, and the input voltage is 4 volts now. So then what will be the positive half cycle is applied? What is the output positive half cycle swing? So they are just they want to know what will be the positive half cycle swing. I'll just say here, keep in mind the concept of range of feedbacks. Range of feedbacks. That will be enough to solve this question. So this question was okay. Uh, then yeah, we'll move to the next question. A closed loop op-amp amplifier has a gain of 100. So closed loop op-amp amplifier has a gain of 100 and a bandwidth of 1 megahertz. Now the gain is adjusted to 200. Now we are saying that the gain is what will be its bandwidth. So we know that bandwidth yeah, bandwidth at frequency So gain bandwidth product frequency, we have gain 1 megahertz. So that means the gain is 1 there. So 1 into 1 megahertz, we can get any amplification, like any gain at that corresponding frequency. So for that frequency, so this is the gain at that particular frequency, this one, and we have gain of 1 at this. Okay, no, no, sorry. A closed loop amplifier has a gain of 100 and a bandwidth of 1 megahertz. Okay, now the gain is in 200 what its bandwidth. Oh, sorry. This is we have interpreted this. This is not like this. So we have 100 as the gain, and we have 1 megahertz at that particular gain frequency. Now we don't know the gain is, now the gain is adjusted to 200. Now we don't know the frequency. We can easily get the frequency from there. Okay, so based on the this, you can do this. Then how many RC stages are used in RC phase shift oscillator? What is the phase shift provided by the feedback network? So RC phase shift oscillators, we know this is self-explanatory. We know just uh, like discussed also. So this is there. So you can easily solve this question. Okay, this is a very easy question. So now move to the seventh question. So seventh question is saying that the following options are all model numbers of different types of op-amp based ICs. Get hold of the data sheets. So they are asking us to like check the data sheet and analyze them. Which among the following ICs would need to be avoided for high frequency applications? That means like the op-amps, or we'll say ICs having less bandwidth. We have to basically see the bandwidth of them in the data sheet. So whichever is having less, we'll have to avoid that for the higher frequency application, because we need to use this circuit, these ICs in high frequency applications. Okay, so that is there. So we have LM741, LM318, LM218, LM35, LF351. So uh, I have the data sheet of these ICs, and we'll just discuss. And we'll see also like how this data sheet is looks like, and like how we read that and all that. So first of all, okay, we see that the title is LM741 operational amplifier. We are starting with LM741. Okay, so we see some of their features that overload protection is there on the input output. Okay, and latch up when the common mode range is exceeded. So that is there. So these are the features. So application, if we see comparators, multivibrators, DC amplifiers, we see summing amplifiers. We know now integrators and differentiators are there. Then active filters also are there. Active filters we learned about. Comparators you also know. Multivibrators, I think you will be learning in future of this future lectures of this course. The DC amplifiers you saw, summing amplifiers are again easy. So these are the applications there. Then we saw that this is typical application of this op amp. Like it can be used as a positive, or we'll say this is non-inverting amplifier. Okay, so this was there. So input is there. So we'll get this. So now they said. So yeah. So now the one who joined here, I'm just discussing about the this data sheet LM741, because one of the questions like this mentioned like we have to find the high frequency application ICs. So for that we will have to look in the data sheet of that, and for that like I'm going through the data sheet. Anyway, you can high frequency application, you will have to look for the bandwidth of that IC and in the data sheet. So but I'm giving you a overlook of what this IC is, what all information is contained in this data sheet of any particular IC. So here, like as we saw, there were some applications for this IC, and then they gave some typical applications of where this IC can be used. So it can be used as non-inverting amplification. I like in this thing. So then We move to like, so there are some pin configurations. So every IC comes in this form. So this we say PDIP or CDIP. So there are each and every pin is designated like used for particular operation. So we on this IC is good also because there is an option for offset null also. It is insert. We saw this offset V offset thing and all. So there, like if we'll use these two pins, 1 and 5, we can make this offset null also. So that is one good part for this IC. So then we have all these things, inverting, non-inverting, offset, null, and all those things. Then yeah, this is important. Supply voltage we can give for these two ICs. We can give till plus minus 22. Then for LM741 we can give plus minus 80. Then there is differential input voltage. Input voltage we can supply. We can give till plus minus 15 volts only. So these are the limitations. These are the maximum readings which are being decided for an IC. So these the people test these ICs and then they'll decide these conditions. So this was there. So operating temperature, junction temperature. So we are interested in what, we are interested in the bandwidth. So let's say, oh, before that we'll see 5 millivolt is the offset voltage here, and we have offset current also, which is nano amperes. Okay, so this is there. So then input bias current is there, and input resistance and all those things. Now we have bandwidth, where the bandwidth is somewhere here. Bandwidth of this power we have slew rate also. So here it is the bandwidth. So you will have to look at this in order to say till what range it can successfully, so this successfully amplify the signals. So yeah, so but you should know other parameters also, like what is voltage swing, short circuit current, common mode rejection ratio. Like this is also required, supply voltage when you are like precisely making a circuit which you cannot bear even a single noise also. Then then you will have to consider these factors also. Okay, CMRR is very important factor in considering that thing. So these were the things. So this is like we know every op-amp is made of basically transistors. So these are the building blocks of an op-amp. So this is the circuit layout of that op-amp, and then yeah. So open loop, closed loop configurations. So this was a typical example of that. Yeah, detailed design. So here, yeah. So then there was another IC was LM318. So LM318, it is I think better IC because in some ICs they give bandwidth in the starting itself. So you can say you can get the features in the starting. So this is very good slew rate, 50 volt per microsecond. Initially LM741, how much slew rate it was having? It was I think having very less slew rate. Fluency, student only zero point 0.5 volt per microsecond. It is very less in compare, and we need, you know that we need high slew rate in order to like process that input signal fastly, so it don't get distorted. So this is very good slew rate here, and like supplies are almost similar in comparison to the previous IC, and this is a configuration where like this capacitor is used to compensate for what will say uh, uh, stability, like to achieve the stability. So this capacitor is being used in the feedback. So this you can learn, but this is out of scope of this lecture, of this course. But these capacitors are used to basically stabilize this op amp. As I can simply, I will just tell you a very raw method. Like if we have an open loop gain characteristics like this, so because of some parasitic capacitance here, so this is a parasitic. Parasitics like we don't know from where this capacitance is arise. So they normally this is a parasitic capacitance. Parasitic. So we in order by this capacitance there is like there is like another. So this is basically frequency. This is frequency. This is gain. Because of this parasitic, there is another characteristics. Okay, so what happens when we look at the phase? The phase, this is the basically Bode plot. So these are the frequency response and this is the phase response. So phase can tend to become 180, minus 180, 180 you can say, and they had this junction. So here, like to avoid this thing, this actually goes down. So this like yeah, somewhere like actually no, this is like this only. Uh, so yeah, so here like the circuit becomes 180. The phase for the closed loop phase for the circuit become 180 degree, and you know what happens in 180 degree. The output will start oscillating. So it become unstable. So that's why they use this capacitance, feedback capacitor to avoid this instability. So we were yeah. So back to the topic, we were looking about the bandwidth. So bandwidth we got. So slew rate we this is a very good slew rate op-amp. And input resistance if we see that is like see very high, 3 mega ohm. So it is good. We can expect more also from better ICs have like much more input resistance in this. So that was there, and then yeah. So this was there typical and yeah these are now just going through these typical performance characteristics. So with the temperature, this input current it changes. So this is the like supply voltage it will change. So and the voltage gain that will like if you change the supply voltage and the voltage gain. So these are based on temperatures. So that also varies a little based on the temperature. But normally we use 25 degrees Celsius, so that is like okay. But the important thing I want to do this like frequency. If it increase the frequency, the supply rejection ratio will go down. And if this is going down, then from the power supply. So since we are giving input, we are giving supply to this op amp. Okay, this VCC and this is minus VCC. So there is a chance of noise entering from this power supply that can hamper your signal. So this is what it is showing like this capacity, this op amp can is good at low frequencies. It can easily reject power supply noise up to 70 dB at 1 kilohertz. But if we talk about if we go for higher frequencies than at 100k, what happens? It is only 40 dB, and even higher, like at bandwidth, the bandwidth is 15 megahertz. Okay, it is somewhat here. Oh, sorry, so it is sorry here. This is the bandwidth where the gain is one. What was the bandwidth? We'll just check it. 15 megahertz. Yeah, so 15, it will be somewhere here, sorry, it will be somewhere here. So basically, but if you talk about the gain one, like, so here it is like, it is at the supply rejection ratio is 0 dB only, like, it is very poor in this condition. So this is like frequency and the noise, as we increase on frequency, the noise also increases. Then we have, yeah, this is very important, this thing, common mode rejection. So there is a trade-off. If we want to go for higher application, this CMRR will be poor. The rejection ratio will be poor. If we let's say if we are working on 100k, so it is only 70 dB in comparison to 1k, which is like 90 across almost 100 dB. So what happens if we have low CMRR? If CMRR is low, then noise is normally behaves as a common input to both the channels. So it will amplify. So this is let's say if this is the noise signal, here it will got amplified and it will hamper our output signal V naught. So this is not good. So we need to go for higher bandwidth signals, higher bandwidth op amps for this. Then one more important thing was there, voltage gain frequency. Yeah, open loop frequency. This is also very important characteristics. So normally we go for small signal analysis. So this also, but yeah. So if we see here, so this is frequency. So see, frequency keep on changing and the gain keep on decreasing. So if there is a low voltage gain, what will happen? So why this is important? Let's say it is only 20 dB voltage gain. So the virtual short will cease to show the virtual short concept, because virtual short concept depends on high depends on high open loop gain. If the open loop gain is not high, then this then what will happen? This virtual short will not be there, and op amp will not be able to show its ideal. It will cease on showing the ideal characteristics. So we this regions are good. Like till 10K also it is fine, but after that it is like the gain is decreasing. Okay, so that is there. And one more thing, if you see the phase, this phase plot is going like this. So somewhere it will reach 180 degree. So when it reaches 180 degree, it is near what we'll say, let's say 70 megahertz. So there, if it is 180 degree it reached, then it will become unstable. So that is also like we have to keep in mind. Okay, so these are the things. Output swing was there. So these are like important characteristics when you see in an op-amp. Like when you are buying an op-amp, you should look. This is important open loop frequency response, and this is CMRR. This is important. So these two characteristics you should really look. And yeah, so rest, yeah, you can go through. These are all for different. Then we then we had LF351. It was okay, smooth. It was okay for the 16 volt per microseconds, and this is a JFET based op amp, and it looks like this. See, and if we talk about bandwidth, then bandwidth is also, we'll see, gain bandwidth further. See, it is this one. So based on these things, you can able to answer this. Okay. So then next question was, what are the capacitors and inductors in Hartley and Colpitts oscillators respectively? This is very easy question. Why Hartley oscillator is not suitable for low frequency range? So you can say low value, so stringent resistance value requirement, low value capacitor difficult to get low value. So if you will just think like if you would have gone, you would have attended laboratories in your BTech. Yeah,
Excuse me, sir.
yeah. Tell me.
Yeah, can you go back to the previous question? Number of inductors and the capacitors and colpits and hotly asked. How to understand this question?
This one.
Yeah, that one.
What is the number of capacitors? See, you simply see the circuit of Hartley, and I will show you. Made the circuit.
Yeah, see, I know the circuit. It has
Hmm.
the colpits has the two capacitor, one inductor. Hartley
Hmm.
has the two inductors, one capacitor.
Yeah.
But how to understand this question? What does that
Understand.
mean? A
What
number
are?
of capacitors and inductors in Hartley and colpits means that
Oh, okay.
capacitors in
So
Hartley
okay.
will be.
Okay. So
Uh,
you are like there's a problem in understanding the language of the question.
yeah.
Okay. Wait. I will read it again. What are the number of capacitors and inductors in Hartley and Colpitts? So they are talking about capacitors in Hartley and inductors in Colpitts, because they are saying respectively. Yeah, it's a
Okay.
little tricky based on this.
Uh-huh.
It's little
Yeah, it's a
tricky, yeah.
lie. Actually, question is that the two inductors, one capacitors, and two capacitor, one inductor is there.
That is there.
But how to understand this question? Because my answer was wrong for this question. Because I know
Okay.
the answer structure,
Yeah, got it.
still I got the.
Yeah, in these things like so in this way you will understand. I think then the answer is right. Capacitor is
Uh,
one,
uh, uh,
then
uh.
it is one. So yeah,
Yeah.
so normally yeah, actually the question should be clear but clearer. Yeah.
Okay.
So when you are saying
Okay.
respectively, na, so it's like
Mhm.
whatever this is the subject you are talking about, and this is
Yes.
like for what you are talking about. So like if there are two
Yeah.
things, so it will come for each and everything. So
Uh.
yeah, it's more of an English talk.
Okay. Thank you.
Yeah. So yeah, then this was the ninth question. Which oscillator use both feedbacks? This is also very easy. So after this, I will. So there was one doubt for like most of the people in that. Uh, yeah. So there was a doubt regarding. I will tell you. Yeah. So there was one question where sir used RC phase shift circuit using three resistors only, but actually initially which like he told about four resistors. Like one resistor was in the input terminal of the negative side of the negative terminal of the op amp, and then three RC circuits were used. But then like three resistors were used, and then the phase shift RC phase shift circuit was being realized. So how we will like just to clarify that out, I posted a PDF also in one of the answers, you can look. But uh, I will also derive that whole thing here. so that you should not have any doubt in like why the how that gain came. That gain came around, it was RF by R. Okay. So and here there was no RI. That is RI is the inverting amplifier resistance, inverting amplifier input resistance. It was not there. Input resistance. Okay. So it was there. So we were being taught this circuit. I'll just make it clear. Minus plus, so this was grounded, this was a capacitor R, so these are grounded. Okay, so this was there, so there were like three resistors here. This was RF, this was RF, but instead in the question it was being solved for this grounded, one resistor here, one resistor here, then one capacitor, one resistor, one capacitor, one resistor, and then one more capacitor. Yeah, yeah. So this is, it was like this. Okay, so we will solve this like based on this. So this was 3 hours here. This was RF, and the gain was given as RF by R. So how we'll do this? So I'll just solve it for you. See. So who had this doubt, they can see this thing, and then yeah. So it is little bit lengthy. So have patience. We'll slowly solve till the end. Okay, so yeah, so in order to uh, I will first make the circuit properly. So this is a circuit, we can make the circuit like this: capacitor, then one more capacitor, then yeah, then one resistor, then this is there, minus plus, then this one, this is RF, this is R, this is R, this is R, this is grounded, this is grounded, and this is the positive feedback being given to this. This is the positive. This one is positive feedback being given, and this is the negative feedback. So I'll just for clarity, I'll just remove this anything. Yeah. So now we have capacitor C, C, C. I will mark these nodal voltages as VB. This is, we'll say VA for simplicity. This is I2, this is I1. Although this is like just, this will not, this derivation will not come in the final examination or something. Just for the understanding, I'm telling you. This is I3, this was I4, and this voltage we will keep as V. Okay, and this is, we know, V by R. Why V by R? This is 0, this virtual short, this is 0, and this is V voltage, so the current through this is V by R. Okay, self-explanatory, nothing is there. So now for this is V naught. Okay, now for simplicity, for calculation basically, I will break the circuit from here. I break the circuit from here. Then I will keep this as V naught prime, and this I will keep it as V naught. So this will become V naught prime because this is being attached to it here. So this is the circuit, and this circuit we will analyze. How we analyze? We'll simply use KVL and KCL. Okay. So yeah. So we'll start with KVL at node A. KVL at VA. KVL at VA. VA is there. So VA minus, we can write V by R is the current through the capacitance. So that is 1 by SC. We are solving in the S domain. Okay, which is equals to V. So this was the circuit. This is VA, this is capacitance, and this is like, yeah, this is V voltage. So here we are applying KVL. So this is there. So VA will be V 1 by SCR plus 1. Okay, this is one thing we got. After that, we'll apply KCL at node VA. KCL at node VA. So VA is what? This code, node VA. Okay, so I'll just draw a VA node here. So VA is capacitance, one resistor, and again capacitor. This is VA, this is C, this is VB, this is what? I3, this is grounded, this is resistance, this is I4, this is V. Okay, so now simple current equation I3 equals to I4 plus V by R. So here it is V by R, current going from this branch. Fine. Then what is I4? I4 is simple VA by R plus this is what V by R, simple. Then we have I3 as V into, we know VA from this equation. So we'll substitute that and we'll get 1 by SCR plus 1 by R plus V by R. So it is equals to 2V by R plus V SCR square. Fine. So this we got I3 in terms of V. This is one. This is another equation. Okay. Now we'll solve for. I'll add some pages. Edit page. Add. We'll add some. I think 4 pages. Fine. Okay. 4 pages added. Uh, yeah. So I will just write it here also. So now I2. What is I2? Uh, I2 is VB by R. How? I2 is this one, VB by R. Okay, I2 is VB by R, simple. So we can write VB as what? VA plus I3 by SC, simply using KVL at this line. So it will be divided by R. Okay, so it will be V. So we are substituting VA from the previous equations. 1 plus 1 by SCR plus 2V by R plus V divided by SCR square by SC divided by R. Okay, so this is I2. This was there. Then finally, after simplifying V by R plus I2 will become V by R 3V by SCR square plus V S square C square R cube I2. Okay, now we will apply KCL at, so we got I3 here, we got I2 here. Fine. So then we will apply KCL at node VB. KCL at node VB. So what is that? I1 equals to I2 plus I3. I will draw KCL node VB here. So it is like this. See. So we are simply moving to the like previous RC circuit. So first we solve for this one, then this, then this. Okay, we'll step by step we are going. So this is R, this is R, this is grounded. So we have C, we have VB here. Okay, this is what V naught, this is I1, this is I2, this is IB. Okay, and then this is VA. So we have I1 equals to I2 plus I3. It is simple. I1 equals to I2 plus I3. Okay. So then this will be simply we are using I3 and I2 from here. We got V by R plus 3V by SC R square plus V upon S square C square R cube plus 2V by R plus V by SC R square. Okay, now so we got I1 also. Now VB is, again we are using KVL in this thing. So we'll get VB equal to VA plus I3 by SC. Okay, which will become after solving V, after substituting all the values, we know VA, we know I3, we finally got V plus SV 3V by SRC, V upon S square C square R square VB. Fine. Now finally calculating V naught, what we have, V naught equals to VB plus I1 upon SC. Okay, so this is there. Then what we'll get after substituting VB and I1 from the previous equations, we will get V plus 6V SRC plus 5V S square C square R square plus V upon S cube C cube R cube. This is V naught. Okay, this is there. So we got V naught as this. So this is V naught. Now, what is loop gain? So now we'll think what is. Now we'll talk about loop gain. So loop gain is A of S, beta of S, which is what we'll see this. So this is V naught. This is V naught prime. So loop gain across this is V naught by V naught prime minus V naught. Sorry, V naught prime by V naught. Since this is in inverting form, this is input is being given to inverting terminal. So this will be what minus V naught prime by V naught. Fine. So if we can so V naught is what? V naught prime is what basically. So V naught prime is coming. Okay. Yeah. So V naught prime is coming from the this simple this circuit, inverting amplifier negative feedback circuit. So what is that? That is simple minus RF by R. Okay, this is plus minus RF by R. This negative is already here into V. V was the input voltage at this node. This is V. Fine. This we got, and V naught we can substitute from here. So this is V plus 6V SRC plus 5V upon S square C square R square plus V upon S cube C cube R cube. Till now it's fine. Then if we substitute S equals to j omega, finally we will get an expression A j omega beta j omega as what minus j omega cube. This is simple than maths. Rf by R 1 by C cube R cube minus 6 omega square by RC plus j 5 omega by C square R square minus omega cube. Okay. So now for phase shift to be 0, now since this circuit is for phase shift to be 0 to meet, so as to meet Barkhausen criteria, Barkhausen criteria, what we have, we have to make this part 0. Then what will happen, this if this will be 0, then this and this j will cancel out and we will get, yeah, so we'll get a phase shift of 0. Okay, so by using that we'll get 1 c cube r cube minus 6 omega square upon rc equals to 0. From that we got finally f naught equals to 1 by 2 pi root 6 RC. So now things will become familiar, as this is uh, the frequency of an RC three phase three RC phase R3 RC circuits for phase shifting. So this is what we actually saw. Okay, and this is what, so yeah, so that implies omega naught is 1 by RC root 6. Now at omega equals to omega naught, what will happen? A beta will be minus RF by R by 29. This will reduce to 29. So now, so this is how we got this. So if you'll see, for mod of A beta greater than equal to 1 according to Barkhausen criteria, we need RF by R by 29 greater than equal to 1. That means RF by R should be greater than equal to 29. So that's why in the question we use 29 and we use the gain as RF by R. So we use then this equal to 29. So this is from where it came. So now you can recall from the question which was being solved in the class, in the lectures. So here how this RF by R came, and we solve that thing. So this hopes this clears your doubt. So after this, it's all like there are some few questions like based on oscillators. So we'll solve this to get a better understanding of like they are not only IC, like there are like these standard oscillators also, but in form of question we will see how we can realize oscillators. Like this oscillator is being realized using LC circuit. So how what is the function, how it is functioning, how it is behaving, we'll see by solving this question. Okay, so just read this question. So these are basically extra questions. I will write extra questions which will provide you understanding of the concept, and yeah, by practicing these questions, yeah, you will be able to get an intuitive feeling of oscillators and all. Okay, so yeah, what the question is saying, we'll see. So this is a this is a sinusoidal oscillator formed by placing a second order LCR bandpass filter. So this is a second order LCR bandpass filter. We'll see how it is by when we'll realize the transfer function of this. So in the feedback path, this is a feedback path we are using, and so L, C, and R is there of a positive gain amplifier. So this is a positive feedback, positive gain amplifier. Positive gain amplifier is being achieved from this R2 by R1. Find the frequency of oscillation. So they are asking to find the frequency of oscillation W naught. This is W naught. W naught, and the condition for oscillations to start. So they are asking these two things: one, frequency of oscillations, and then conditions of this oscillations to start. Let's remove this whole thing. Okay, so they are asking frequency and then they are asking conditions. So and they are saying assume an ideal op-amp. So how will approach? So we know. So first you will think, okay, how we can do, like we know that Barkhausen criteria is there in our mind. So we know that some mod A beta is greater than equal to 1. That is there something. So yeah. Okay, okay. So yeah, so so I'm discussing this question, like this is question. You can read this question. So this is basically a sinusoidal oscillator which we are realizing using LCR circuit, second order LCR bandpass filter, and we want to calculate the frequency of oscillation and the condition for oscillation. By the way, these are the extra questions. Uh, it will help you understanding these concepts more nicely. So yeah, so how we will approach this question? So we know that okay, there is some Barkhausen criteria, mod A beta greater than equal to 1. So can we use that? So yeah, we'll use that only. So for that we need A and we need beta also. So what is it? The gain of this amplifier, we can simply say it is V naught by Vi, which is equals to 1 plus R2 by R1. This is small r1. So this is like the gain because of this negative feedback. Okay, then we need what is we also need this beta, the feedback, the positive feedback. What is beta? Beta of S. So how we'll do that? So beta is, we can say this is the V reference of V feedback voltage. V feedback voltage. So this is VR by V naught. This is beta factor. Okay, how much fraction of V naught we are getting? That is like that is what beta is all about. Okay, so if we use nodal equation here, we can get VR by SL plus VRSC plus VR minus V naught by R equals to 0. So this is one branch, this is one branch, this is another branch. So we have simply used nodal. Node at, let's say A, at A, we are using that. So we got this. If we'll simplify this thing, what we'll get? VR by V naught. So we are basically, yeah, in S domain we are solving this. So this will be S square LRC plus SL plus R. So by this equation itself, you can say why this is an LCR bandpass filter of second order, because you are getting a power of 2 in the denominator, and this is an equation of second order. This is a characteristic equation of second order. So yeah, so this is there. So it will more simplify this. This will be S by RC, S square plus S by RC plus 1 by LC. Simple. Okay, VR by V naught we got. Now if we can simply calculate AS and BS beta S. So this will be what? This will be, we know A of S is what? 1 by R2 by R1. We know what is beta. Beta is S by RC divided by S square plus S by RC plus 1 by LC. Okay. Now if we, okay, I will use this page. This, if we substitute S equals to j omega, what will happen? This will be A of j omega, beta of j omega will be equal to 1 plus R2 by R1, j omega by RC. So this will be minus omega square plus j omega by RC plus 1 by LC. Huh. So how will get phase 0? So for phase to be 0, since we need to achieve this Barkhausen criteria where we say that the phase should be 0 for the feedback circuit. So for phase to be 0, how we'll achieve this? We will achieve this by uh, the real part of denominator. If the real part of denominator, this one, this denominator, we can make it equal to 0. If we can make it like this, so what will happen? Then minus omega square plus 1 by LC will be 0, and this j and j will get cancelled out. Okay, so that's why it will be like omega square equals plus 1 by LC equals to 0, minus 1 by LC equals to 0. That implies omega equals to 1 by root LC. So I'll just add one more page here. Edit pages. Add one page. One landscape. Okay. So we saw the oscillating frequency for this oscillator will be 1 by root LC omega naught. Oscillating frequency. Oscillating frequency. Okay. Then now we need also they asked also this, like what are the conditions for the oscillations to start. So now we can use this in our mod of A beta. Since mod of A beta will be what? 1 plus R2 by R1. Since the real part of the denominator will be 0, we will be left with j omega by RC in the numerator, and denominator will be having also j omega by RC. So this will get cancelled out. We will get a gain of 1 by R2 by R1. Okay, so in order to be meeting Parkinson criteria, they should be greater than equal to 1. So that means R2 by R1 should be greater than equal to 0. So these are the condition for uh, yeah. So this is the condition. So basically, if we also like, or we can say if we achieve a gain greater than 1, then we can, because initially we need the gain to be greater than 1 so that the oscillations can start. So if we can get gain greater than equal to 1, we will be able to achieve the oscillations in this oscillator circuit. Okay, so this was all about this question. Then there is another follow-up question for this. They are saying in the previous question, find the percentage change in the oscillation frequency resulting from the change of plus minus percentage values of L, C and R. So like when you in reality also, when you use one inductor or capacitor or even resistor, your resistance, you know that there is tolerance in that. In inductor, There was one question also in assignment, like based on this, like inductors are having their impact. They have some resistances, series resistance in them. Capacitance, they are not perfect dielectrics. They are not perfect dielectrics, so they have some leakage through their plates. So some leakage is there between them. So based on these practicalities, so if you are even taking 22 let's say there was a reading of 22 microfarad on a capacitor, it will not be 22 microfarad when you will be measuring from a meter. And the meter from which you are measuring, that itself contains some impracticalities because of its internal circuitry. That's why there can be some tolerances. So then we should see, like, if there is some percentage change in these values, so how much it will affect our frequency. Basically, how much it will affect our the circuit which we designed. So let's say you design this oscillating circuit, and you are, let's say you are making a function generator. For that you need this oscillating circuit. Okay, so then, how much imperfections these things, these values of R, C, and L can add up to your circuit, and it will finally show in the output. So you should be knowing all those things about it. Like, you should be knowing about these things. So for that, let's say we'll take first case when L changes to there is let's say plus 1% change in L. So what will happen? L prime will be L plus 0.01 of L, so it will be 1.01 of L. Okay, so then omega naught prime will be what? 1 by new capacitance, new inductor is 1.01 L into C, which is what? 1 by under root 1.01 into omega naught. So this is what? This is omega naught. Okay, so this we can say in terms of omega naught. So then what will happen? So percentage change in omega will be given by omega naught prime minus omega naught divided by omega naught into 100. So what will be this? This will be 1.01 omega naught minus omega naught by omega naught. Okay. So this will be what? 0.01. So this will finally become 0.5 percentage change. So this much percentage change will be absorbed in your oscillating frequency. What if it is a capacitor, C changes to plus 1%, then C prime will be C plus 0.01 C, 1.01 C. So omega naught prime will be same, omega naught by under root 1.01. So then percentage in delta omega will be same, 0.5%. But one good thing in this is that our output frequency, the oscillating frequency. So if we talk about the resistors, there is a, like, what if there is a 1% in resistor? Since omega naught is 1 by LC, it is does not depend on R. So percentage change in delta omega will be zero. So this is a good thing. Good thing for the circuit. So when you were designing this circuit, so you designed this circuit. So what was the advantage of this circuit? Like, it is not being affected by this R value. So even if you, like, there is some tolerance in this R, if there is a high tolerance of 5% also, then also the oscillating frequency of the circuit will not be affected. So this is good for the circuit. Good for the circuit. Okay. Yeah. So this was about this. So now there is another question. This is kind of similar, but we change the configuration of the feedback circuit, positive feedback circuit. So now we are using RNC. So how will that, again they said that the frequency for, like, what will be the zero loop phase frequency, and this is by the way the loop gain. This is loop gain is there, and this is R2 by R1 for oscillations, and R2 advance as in the Opamps value. Yeah, frequency for zero loop phase. So they are also asking for the what will be the oscillating frequency for this oscillator. So since we as we approach in the previous question, this one, we'll see this question also. First read this question. So now we'll approach again like that only. So what will happen? We know A equals to what? A is V naught by Vi, which is equals to 1 plus R2 by R1. Okay, this is because of the negative feedback. This is here Vi is. So this is a gain of a positive in non-inverting amplifier. So then, what is beta? J omega, or we'll say first beta. It is Vf by V naught. This is Vf feedback voltage. Okay, this is Vf. So what it will be? It will be simply using nodal here. We'll get we'll use KVL at node V2. We'll say V2. We'll say not V2. Wait. So yeah, KVL at node VI. This is VI. So this is V2. So KVL at node VI. What it will be? It will be, since this node Vi is basically Vf voltage, so this is Vf SC, this branch and this branch, plus Vf minus V2 by this, let's say Vf. This is Vf voltage. V2 by R equals to 0. Based on that, we can get V2 equals to Vf 1 plus SCR. Okay. Then, if we use KVL at node V2, what will happen? KVL at node V2. It will be V2 by R, simple. One this branch, one this branch, one this branch. Okay. KVL V2 by R, V2 minus Vf by R plus V2 minus V naught by SC equals to 0. So if we'll solve this, we'll get V naught by Vf equal to S square R square C square plus 3SRC plus 1 divided by SRC. Okay, so then beta, the feedback factor is what? Vf by V naught. So we'll get SRC divided by S square R square C square plus 3SRC plus 1. Okay, so if we use beta of j omega, as we are using S equals to j omega after this, then we will get Vf by V naught is what? 1 upon, after substituting, we'll get finally 3 plus j omega rc minus 1 by omega rc. So again, to make phase 0 degree, we need this to be what? 0. Okay, that will make omega naught, that is the oscillating frequency, equal to 1 by rc, oscillating frequency for this for this oscillator. Fine. So we got this. So then what will be beta? Beta will be 1 by 3 at omega naught. And we know mod A, according to this criteria, mod A beta is greater than 1. That means mod A is greater than 3, since we have beta equals to 1 by 3. So for this circuit, and what is A? We have A is 1 by 1 plus R2 by R1, which is equal to, greater than equal to 3. For this circuit, we need a gain of little bit more than 3, so that to make the circuit run in oscillations. Fine. So yeah. So this was there. So this was like so these were some questions. These were some extra questions which we discussed to get a better understanding of what, like how you can solve a circuit having both positive and negative feedback, because this is having a negative feedback also and a positive feedback also. So how you will analyze those circuits. So by that you can use frequency, like you can calculate frequencies also. So we'll just quickly go through what we learned today and what was being discussed in week 3. So first we talked about clampers using Opamp. So there were positive clampers and negative clampers. Positive clampers can clip the can insert the DC and can clamp the voltage to the positive side, and the negative clampers can clamp the voltage to the negative side of the circuit. Then we analyze this circuit, like how this clamper worked. So for that we use superposition principle. We first consider Vref, we got V naught. Based on that, then we considered Vs. Then we got uh, what we got? We got again V naught double prime, and after that adding both two, we got the final this output voltage for us. Then we saw that in the lecture, like there was some blunt ends were there for the circuits. Like why, like this, why were these there in the circuit? Because of the this there was some this diode was becoming forward bias for the voltages greater than for the voltages for this negative inverting input side terminal voltage getting less than the reference voltage. Based on that, for that this was becoming forward bias, and then we were getting a clipping action here. So that was the so then we saw the range of feedback amplifiers. So how this range of feedback amplifiers are decided? These are based on the supply voltage which we are giving to the op amp, and then the gain bandwidth product of the op amp also it is decided. So we cannot kept on increasing the frequency as it is being limited by the gain bandwidth frequency of that op amp, and also we cannot kept on increasing the gain or kept on increasing the input voltage as it depends on the supply voltage of the op amp that is there. Then we see in the further lectures that op-amps, how the oscillators are being realized using op-amps. So oscillators, why they were being used? So they were being used in clock circuits, for synchronizing various stages also. Then positive feedback. So they use basically positive feedback. There can be combination also like Bain bridge oscillators. Then we see that these convert DC input to AC signal, and we need again slightly higher than 1, normally higher than 1, so that it can achieve the oscillations, and by a op amp we can sustain that feedback, that oscillations. So that was there. Then we analyzed the basic circuitry of an amplifier circuit with a feedback, and we saw Barkhausen criteria. Then there was phase shift oscillator, we studied about them. Then we got their frequency, why they were then Wayne bridge oscillators, then Hartley oscillators we studied, then Goldfield oscillators. Then we discussed the assignment questions. Then we discussed about some data sheets also. Those were like LM741 was there, this one was there, LM318 was also there, and LM351 was also there. Then after that, we there was some doubt in the session in the discussion forum, like we were taught this RA based RC phase shift circuit, but instead in question they were using only 3R circuit. So where this RI gone? So for that, uh, we derived the equation for only 3R circuit network of the oscillator. So you can go again through this derivation. Okay, so we use some KVLs and all, and finally we achieved this. We achieved this gain. This gain we achieved finally. So this will give you a better understanding of the question we solved in the class. Then we solved some extra questions also, so which were based on some oscillator like LCR second order LCR bandpass filter it was, and then we saw how it these we got the oscillating frequency, we got the gain limitations, like gain like limitation in the sense that when the oscillations will be starting, and then we see how the percentage change in L, C, and R can affect this oscillator, which we just solved in this question. Then we again solved another question with a different feedback, which was using R and C in this. So this was all about this week's session, live session. I will this session will be recorded. You can see this in YouTube also. So yeah, thank you. Any doubts? If no doubt, I will leave this call. I will end this call. Thank you. Yeah, we'll meet next Tuesday this time, 6 to 8. Yeah.